Okay. In this lecture, I will go over trees, random forest bagging, how to implement it in R using some simple examples. Example, the data we'll use is from the mass library. This is the Boston data set. So we're trying to predict the median house price based on the rest of the predictors. So we split the data into two pieces. We do a random sample of the indexes from 1 to n. So and then we fit a tree. Let's do this again. We need to call the library obviously. Okay, so now we have a tree. And we can get the summary. So what is the deviance here? Excuse me. The deviance here is the sum of the square root of errors for the tree. And only these three variables were used to construct the tree. We can plot the tree. This is how the tree looks like, and then we can also this is a easily interpretable tree. We have these variables depending on what the variables are. Then the median price will be 21, 27, 18, 14, 10, 33, or 45. So what does LSTAT stand for? LSTAT measures the percentage of individuals with lower socio-economic status. So lower socioeconomic status, the percentage of individuals with lower socioeconomic status. If that number is small, house prices are larger compared to those neighborhoods for which the lower socioeconomic status is higher, which is not surprising. So let's see whether pruning will improve the tree. We use the function cd3. And then we want to plot the cross-validation curve. We want to see the cross-validation versus the size. And the cross-validation error is deviance, and deviance for regression means mean squared error. Okay. As we can see, the most complex tree is selected. As we increase the size, the cross-validation comes down, so the largest tree in this spectrum leads to the smallest cross-validation error. Now, we might want to prune the tree anyway. Not that we have a good reason, but in case we want to prune a tree, we use the prune tree function. And we just tell it the size. And then we can plot it. Okay. So this is a prune tree. So let's try to make prediction using the unpruned tree. We call the function predict. We give it the tree object. And new data is just Boston, everything except the train data. I call this y hat test, and then we have y test, which is just Boston data. The median price. Okay, so we're saying the column med V, which is the median price, take that column and all the rows that are not training, this becomes our white test. And then we like to plot the prediction versus the actual. Okay. So, it's hard to see. I mean, it's more or less doing a good job, except for these. And the scales are a little bit slightly different. So 40 to 50, the length is different from 30 to 40. So in order to make that a little bit visible and clearly, so we can see what's going on, we add the line that passes through the line that passes through the origin and has a slope of 1. In an ideal world, all these points would be on this line, but these points that are off, these are the residuals essentially. This distance from each point from this line tells us how off the prediction has been from the true observation. And the mean squared error is just okay. And this is how off it has been. So just run everything from the beginning again. Okay. So and what is the square root of this? So on average, this model leads to a test prediction that are within $5,000-6,000 of the true median home value for that suburb. Okay. The next is bagging and random forest. We need to call the library random forest. We set the seed. We call the function random forest. The median price versus the rest of the predictors. The data is Boston and the subset is train. Okay. Okay, so this M here is the M that random forest uses. Remember, random forest for each split, we can give it this extra parameter M, which restricts the predictors. So at each split, a tree, when we grow a tree, for each added split, we looked over all the predictors we have. Now, random forest chooses a subset, and the size of that subset is selected by n try. So try. But left, right? So this is our p. The number of predictors we have is this. Okay. So if we put this equal to p, then we get just bagging. Essentially, we're saying at each split, you're allowed to look at all the predictors. And we want the importance also be calculated. Okay. So back Boston. So the number of trees, meaning the number of bootstrap samples, is 500. You can change that to anything you want, but I think I would just leave it at 500. Number of variables tried at each split is 13, which is we are essentially looking at all of them. And the mean squared of the residuals is 11. Let's see how this bag tree performs on a test set. So we just want the same thing that we have here. Paste it here, except that bag goes down. So you see they are closer to the line, much better. I mean, obviously you have some outliers, but other than that, they're all around the line. And from 5.9, we reduced the error to 4.8. Okay, so now if we want a random forest, we do the same thing, except that here we say square root of p and then lower it, just so it's an integer. This becomes RF. .3, so we further reduce the test error. So we see that 3 is interpretable, but might suffer from overfitting, high variance. Bagging reduces the variance, we lose interpretability, but the trees are still correlated, so the variance should be further reduced. And random forest, when we only allow a square root of p number of predictors be considered for each split of the tree, then we get random forest and we get a better reduced test error. Okay. Now let's look at the importance of the variables. Okay. So we just focus on this one. This is the percentage of increase in the mean squared error. Um, sorry, it's based. This is essentially these measures are based on the mean decrease of accuracy in prediction on an out-of-bag samples when a given variable is excluded from the model. So we have 13%, 2%, 11%, 26%, and you can see the relative importance of these variables. And then we can plot this as well. Arm M and then LSTAT. Okay, so these are simple examples of how to plot, how to fit trees, back trees, random forest, and how to plot the results and interpret them.